So we talked what is a function, what is not a function in the associated terminology, domain, codomain, range, image, pre-images. We talked about types of function. We said the function is injective or one-to-one function if every element of the domain gets a unique image, and a function is onto or surjection or surjective function if every element of the codomain is the image of something, is assigned to something. Okay? And a function is a bijective function, bijection or one-to-one correspondence if it is both one-to-one and onto. Okay? When both of the properties, that every element of the domain gets a unique image and every element of the codomain is the image of something, is assigned to something, then it is if both of these properties are true, then the function is called a bijective function. Okay? So if we have a bijection between x and y, some domain x, some domain y, and let us say we represented the function with the pictorial bipartite graph representation, where we draw the domain on one side and the codomain on the other side, and if x is an image of y, if x is mapped to y, then there is a line arrow from x to y. Okay? So if a function is a bijection and we reverse the arrows, we reverse the directions just from x to y, instead of from the arrows being directed from x to y, we direct them from y to x. What will happen? We get a function. We actually get another bijection, right? And it's very clear to see that why would this happen. This is a function x to y. It's one-to-one and onto. It's a bijection function, one-to-one correspondence. I flip the arrows, I flip the direction, reverse the directions, and I get another bijection. Okay? Let us just see, we will see a few non-examples, then it will be clear why does it happen. Look at this function. This function is this function onto? This function on the left, is it onto? Is it one-to-one? It's not one-to-one. If I reverse the arrows, do I get a function? Or what type of functions do I get if I get it all? If I reverse the directions, if I make the image pre-image and pre-image image in the domain, the codomain and the codomain, the domain, will I get a function? Why not? Can you please, somebody there, you guys, can you please talk to me? If I get a one-to-one function, which is not a bijection, and I reverse the directions, will I get a functions? Why yes, why not, and what type of functions will I get? Why not? One-to-one means, sorry, say it again. Say it again, you're I think right, but I didn't. Which domain? The old one or the new one? I'm flipping the domain, right? The new one. Okay. Yes.
Our new image, the pre-image set will map to multiple elements in the image set.
Okay. Yeah. So we begin with this thing. So let's look at the old function, which is not one-to-one. It's not one-to-one, meaning there are two elements in the domain whose image is the same. For example, here x3 and x4, their image is both b, right? Now, if I flip everything, if I call this, start calling this set a domain and this set the codomain of another function, the reverse function, and mapping is reverse, it will not be a function, because in this particular case, b will get, b will try to get two images, and that's not a function. A function, every element of the domain has to get exactly one image, right? So it will not be a function. Is it clear? If I reverse the arrows. If the function is not onto, is this function on the left onto? Why is this onto or not? Why is this function onto? Is it onto? Why not? F doesn't have pre-image. F is not assigned to anything, so this function is not onto. Now if I reverse the arrows, will I get a function, or what type of function will I get? Will it be a function? Why not? Because then f will not be mapped to anything, right? And every time I get a non-onto function, a non-onto function means there will be a vertex, a point here, who has no incoming arrow. Now, if I reverse the image, the directions, there will be some point which is no outgoing arrow, and exactly one outgoing arrow is a requirement of function by function definition. Is this clear? But if it's a one-to-one correspondence, then none of those problems will occur. Okay, everybody will get an image, and everybody will get exactly one image. Here is an example when the function is both not onto, and not one-to-one. If I reverse the arrow, would I get a function? Would I get a function? What problems will be there in that reverse function thing? What will be the problem? Yes. Yeah, in this particular case, f will not get an image and b will try to get two images, right? So, it is not a function, image word does not go with it, but like f will be like, and b will be mapped to two elements. So, it will not be a function, right? Why does b gets? That is because it is not one-to-one. Why does f have no image under the reversal? Is because the function was not onto. Is this clear? Yes? Yes? Somebody said something, no? Make sense? So, can we say that if I reverse the arrow of this type of function, which is not one-to-one and not onto, can we say that when I reverse it, I will also get a function or a bijection? It won't be a function, right? So, that is the answer. The question says, can we say, can we assert that reversing the arrows of such function will give us a function? But for bijection, I gave you on the top, if you reverse the arrows for a bijection, one-to-one correspondence, we will get a function. Not only we will get a function, we will get a one-to-one and onto function. The reverse arrow, yes please. No, this is f. You see, this is what I say. If f is this function and I reverse the arrows, then can we say that we will get a bijection or we will get a function? No. I say this is for bijection I have told you. And I said, okay, suppose f is not a bijection, f is this function. It is neither one-to-one nor onto. Then can we still assert that the reversed arrow will also be a bijection? We cannot, right? Here the answer will be no. Yeah, so f is not a bijection, it is not onto and not one-to-one. Yeah. Do you see this word? Do you see this word, this sentence? You understand that? If a function is a bijection and I reverse the arrow, I will get a bijection. The reverse arrow thing will be a new thing, it will be a new function, let us call it g. The g will be a bijection, right? Now, I am saying, can we say this? This means this block, right? If the function is not one-to-one, okay? If the function is, so this neither goes with this one-to-one and onto, then it is now neither. Okay. So, this we have established, this is the thing, this if it is a bijection and we reverse the arrow, we get a new function. The new function will be a bijection, okay? This is what in your homeworks, your problem sets, you should be able to give formal proof. The one we just said, okay, if there is no one-to-one, if there is no roommate sharing, if there is no shared images, then in the reverse there will not be more than one image, right? And if everybody is assignment, if the function is onto, then in the reverse there will be at least one image. So, combine those two, you will get actually a one-to-one and onto. The reverse will also be one-to-one and onto function, both a bijection. Yes.
Reversing the arrow could be like a formal terminology. No need to.
Yes. So, abhi aa raha hai. Okay. No swapping is even worse. Inverse of the function. This is called the inverse of function. Finding the inverse of a function when you reverse the arrows. Okay. This reverse the arrow only works with this representation, right? If we haven't represented the function like this, if it's given like a mathematical formula, or if it's given as a list, as a set of image pre-image pairs, ordered pairs, then it will not work, right? But that was just for our understanding. So now we are going to develop this thing. If I have a function x from the domain x to some codomain y, and that function is a bijection, okay? So then I define a new function. That function is from the codomain to the domain, the previous from y to x, okay? And the mapping rule is as follow. If x under f, or if f maps x to y, then this f inverse maps y to x, the same y to the same x, okay? The element x and y to x, okay? It's a b because I didn't want to confuse with this y b, okay? Whenever f of a is b, then f inverse of b is a. Now this is actually what you could, the formal way of saying reversing the arrows, right? F under f, or f says there is an arrow from a to b, this element a to this element b. F inverse is this arrow from b to a, right? If I represent that like this. Is this clear? So if f is a bijection, f inverse is actually the reverse thing, it will also be a bijection. That's what we argued previously, and so this is how you can look at it. So if an inverse exists, then this is what it is. An inverse exists means if f is a bijection. If it's a bijection, then its inverse will exist. If it is not a bijection, let's say either not 1 to 1 or not onto or not neither of them, in all these three cases we can see that the reverse will not even be a function, right? Not that it would not be a bijection, it will not even be a function. Either somebody will not be mapped to something, or somebody would be mapped to more than one, okay? This is how the thing, the f, this is domain of f, the range of f, right? The range and the codomain are the same because the function is 1-to-1 correspondence, the function is onto, right? So if it's onto, then it will be, range will be the same as codomain. That's why I didn't write codomain here. So it's range, then this will be the domain of f inverse. This is the codomain of f inverse or the range of f inverse, because if f is a bijection, f inverse will always be a bijection. And if x is mapped to y, then y will be mapped to x, okay, under f inverse. Make sense? Okay. So let's do a few example and maybe a practice problem, and then it will be. Suppose the function f of x is a function from real numbers to real number, where x is mapped to 2x minus 3. Last time we talked about it. If it is a bijection, then we should be able to find its inverse, right? And it is a bijection, I guess. So is f a bijection? Let's see if it is 1-to-1. If you saw, let's say if it is onto. You look at, last time we said that you pick any element in this codomain real number, any element y and any real number y, and there must be something that this f maps to this y, right? And it is actually y plus 3 divided by 2 is what will be f of y plus 3 divided by 2 will be y. And this is for any generic y, right, arbitrary y. That is why it is, the function is onto. Any real number has a pre-image, okay. Now is it 1-to-1? So let us say we know how to prove it. Suppose x1 and x2 are two different numbers, and so suppose x1 and x2 have the same images, right. So f of x1 is equal to f of x2. Now we know the formula of f, the mapping rule of f, that is 2 times x1 plus 3, 2 times x1 minus 3 is equal to 2 times x2 minus 3. And just do algebra, you get that x1 must be equal to x2. This we did last time, okay. So this f is both 1-to-1 and onto, meaning this is a bijection, right. Now what is the inverse? What is the reversing the arrow thing? If x is mapped to y, then y should be mapped to x. That new function we have to find. What will that be? Yes. So yeah, so this is now you should do the exactly, you solve this problem. So 2x plus 3 is equal to, so we want to do this thing. If f of a is equal to b if and only if we want f inverse of b to be equal to a, right. So, let us see if f of a equals b, that means b is equal to 2 into a minus 3. Okay. Now, we want this thing. So, what should be the f inverse, what should be the a for this b, right. To solve this for a, you get b plus 3 divided by 2 is equal to a, right. So, this is f inverse of b should be equal to okay, that is kind of some algebra you do and you will find it. That is actually reversing the arrow for this thing. Okay. This b and a is the same thing here, b and y and x and a. Okay. Let us do this thing. Suppose I have a function from negative real numbers to positive real numbers. They are defined to be like this, not negative, if r minus is non-positive real numbers and non-negative real numbers, okay. Or you can exclude one from 0 from one side and just call it on the non-negative, but that's not, doesn't make a difference. We know what is there is a set called r minus and there is a set called r plus, right, and the function is f of x equals x squared. Is this a one-to-one function? Is this a one-to-one function? What does one-to-one mean? Can a number, a real number, or in this case a negative real number, a non-positive real number, can it have two squares? F of x equals x squared for any domain is actually a one-to-one function. A number has a unique square, right. But is this onto? Is this number onto? No. So, what did I say? One-to-one? Okay, does everybody gets a unique image? That is one-to-one. No, is generally square a one-to-one function? No, it is not one-to-one function, right. Generally speaking, because f of 1 is equal to f of negative 1, f of 3 is equal to f of negative 3, right. The square of 3 is equal to the square of negative 3. But in this case, 3 and negative 3 both cannot be, they are not part of the domain, only negative 3 is part of the domain, right. Positive 3 is not part of the domain. So, in this case this function is one-to-one, but is it onto also? Is it onto? Remember f of x, x squared, if it was among the integers, it is not onto, only perfect squares are in the, are images of something, perfect squares are in the range, but here it is real. Every number has a well defined square roots, right. Indeed it has two square roots, right. Remember your problem set from yesterday, quiz from yesterday, every number has two square roots, one is positive, one is negative, right. So, in this case it has exactly one pre-image in r minus. So, this function is both one-to-one and onto, so it is a bijection, okay. It is a bijection. So, there must be its inverse. What is its inverse? What is its inverse? If f of 2, negative 2 is equal to 4, what should be f inverse of 4? Negative 2. How do you find this in journal? If f of a equals b, then what should be f inverse of b? F takes a number, squares it, right, take a negative number and squares it. So, f inverse should take the inverse of squaring, it should take the square root of it. But square root gives us two numbers. Now, because we know f is thing, so we will only get the negative square root of it, right. So, this is going to be this is the f inverse of the thing, right. You first have to argue, you can't just start writing formulas. If the function is not one-to-one or not onto or not neither of them, then it will be then there will not be any inverse, right.
Excuse me, sir. Could you explain again how it is onto?
Oh, good. So, let us just think about it. Let us think about this thing. Why is this not onto? So, suppose I have this function which takes in negative integers and returns the square of that integer. Is this function onto? Why not? Can you guys please stop talking?
5 is not a perfect square.
Yeah, so why? Because 5 does not have pre-image. Nothing is mapped to 5, right? There is nothing called square root of 5. Negative square root of 5 is not an integer, right? But in this case, if I make this real number, so let's say this is the same z plus, but this is real, then is 5 an image of something? What is it the image of? Is there anything that maps to 5 under this function? What maps to 5? Oh, sorry, this is by the way wrong. This did not take function like this. Okay, what maps to 5? Not 2.5, the square root of 5. The negative square root of 5, right? The negative square root of 5 maps to this. What maps to 4? What maps to 9? Which is negative 3, right? What maps to 16? Negative 4, right? So that's what, when it's R to R, then everybody has a pre-image. What's the pre-image of 14.37? The square root of 14.37 times negative 1, right? That's what. Got it? Okay. So now function inverse, very important concept, but because we know it so well, the bijection, for us it's just reversing the arrows, okay? No, but you need to practice a lot with this. The next thing I want to do is this composition of function, okay? This is correspond to exactly as a computer science, when we write a function, we call that function, right? And a function can call other function. This is exactly a function. When you write a function and you make it a call to another function, that's actually you are composing these two functions, right? The C++ function, Java functions, right? So essentially, composition of function means applying functions successively, in the sense that you apply one first, and then the output you apply the next function to the output of the previous one, okay? So this is how it moves. So you want to, this is the number x, an element x of the domain, whatever, it doesn't have to be a number, it could be something. You apply f to it, some function g to it, so you get g of x. Then you apply f, the function f, to g of x, right? So you apply, so you apply the function f to the output of the function g, right? So this is what we call composing the function f with the function g, okay? Got it? Composing function f with function g. So suppose I have a function g which maps elements of a to some element of b. So a is the domain of g and b is the codomain of g, and b is that same b is the domain of f, and c, some other set, is the codomain of f, okay? So f composed with g, the composition of the function f with g, f cross g is called, what is it called? F circle g. F circle g, what is it called? What is this thing? How do you pronounce this? Huh?
F composed with G.
F composed with g, okay. So in LaTeX you write f slash circ, you will get this small circle. So f composed with g, f composed with g of number of an element a will be given. So first of all, what will be f composed with g? When I give you a function, the first thing I do is give you the domain and codomain. The next thing I give you is the mapping, right? What element is mapped to what element, or some mapping rule or something. So f composed with g is a function with the domain a and codomain c. Okay, the domain of g will be the domain of f composed with g, and the codomain of f will be the codomain of f composed with g. Yes. Yeah. Yeah, this is both onto and one to one. It is a bijection. No, why not? I just asked that question. What What is the pre-image of 14.37? 14.37 आउटपुट्स में नहीं आएगा, इस फंक्शन के आउटपुट में नहीं आएगा, आएगा का नहीं आएगा? क्यों? Is it clear now? You question clear? Okay. So f composed with g is a function from a to c, and it's given like this. Okay, its value, its mapping rule is given like this. You first apply for any number in a, any element of a, you apply g to it, you get some output, and on that output you apply f, right? And whatever f formula is given, this is what you apply g to x, you get g of x, then you apply f to this number, this element g of x, and you get some other element. That's how we write it, f composed with g of x, or f of g of x. That's how it's pronounced, f of g of x. Okay. Now, please pay attention to this one line. That's why it's underlined here, and this is where you will. The way it's pronounced, the way what is going to happen, what is happening is actually you are writing the code for f. But in writing the code of f, you are calling g. You are calling g function, right? So that's very typical for functions to call other functions. All the functions we write, any code we write generally is what's called in the main function, right? And we call other function in the main function, right? We call print function. We got many other functions. So this is what's going on. Now, suppose. Now, this is important that I told you there must be this thing, there will be some restriction on g. The range of g must be subset of the domain of f, okay, must be subset of the domain of f. Please understand this. Okay. Suppose f is a machine, f is an intelligent machine which is trained on, or f is trained on, let us see the word, that is a AI terminology. Suppose f machine algorithm network is trained on integers only. Suppose f only works on integers, okay, and during its code it called g and g returned negative 18.3. What will f do? F is not supposed to work on non-integers, right? And if you look at this, the code of f, the only thing you see is int, right? Int or unsigned int or whatever you write there, right? Short, those things are written. Now g return double. What will do? What you will get an error? You will get some typecasting error, or you will do some kind of typecasting, or you will get a type error, or whatever. Something will happen, right? So this is exactly what it is. Because we are applying f to the output of g, g better output only those things on which f can operate. Okay? So that's what we are saying, that the output of g, the outputs of g, the range of g, it's even better if the codomain of g, but the range of g must be a subset of the domain of f. Okay? Mouthful of thing, but you know the words domain and range and codomain, but the range of g must be a subset of the domain of f. Okay? Make sense? Because we first apply g, on the output of g we apply f. So if f specifications do not meet, so if you give it an invalid input to f, then f will not work on it, right? The domain is the set of valid input of f. So if this input is not a valid input, f is not supposed to work on that, right? F isn't responsible to do that. Does this make sense? Okay. So keep this picture in mind, please. This picture will tell you f circle g, f composed with g is this function, right? What is this set? What is this set? All of these things please keep in mind, okay? And hopefully it's a very simple concept, but if you do this, let me give you an example. I have a function from real to real which maps real numbers to their cubes. There is only one cube for real number, and we have by the way, square root a function? Square root a function?
Square root? No.
Technically speaking, square root isn't a function. Okay, why? Why is square root not a function? Why is square root not? Is it a function? Say something. Yes.
So it's not a bijection, there are no square roots for
It's
negative.
not. Is square root a function? Yes. So it says the function. So he says one input, two output. That's not a function. Okay. It doesn't pass. What is vertical line?
Vertical line test.
Vertical what?
The vertical line test.
Don't use big words, okay? Just don't scare me. It's just okay. So what is vertical line test? What?
You draw a line upward.
You draw a line and
You draw it upwards from an x point. If it crosses the graph twice from that x point,
oh,
that's two outputs or multiple outputs.
it's such a stupid thing. This Angrez always will just do this kind of thing, this stupid thing. Okay, so I have a function from real to real, which maps its f and it maps elements to their cubes, and they have another function g from integers to integers that maps elements to their squares. Right? Both are well defined functions and stuff. Let's compose them. So f composed with g will be a function from the domain of g to the codomain of f, right? So it will be a function from z to r. This r is actually this r. This z is this z, right? Maybe okay. So this is a function f composed with g. What will it happen? What will it do? On a number a, what will f composed with g do? Or a number x. On a number x, what must be this number? What must be this number? X. It must be an integer. What will it give me? What will it do with this x? F composed with g, what will it do?
It will return a real number.
Yes, but what will which real number will it return? Let's do the C++ operation. What operations will it perform on x? This f composed with g is a function. What will be its steps? What will be executed first and what next?
When g of x is equal to the number square करेगा,
So it will square that x and then
return the integer to the function f.
there is nothing called function f now. It's f composed g. It will take an x, it will first square it, or it will call g and get its output, which is x squared, and then it will call f, which will cube it, and then will return back, right? So the output will be f composed g will be f. First g will be called, then f will be called. So you will get a function f. You will call the function f on x squared, whatever input was there, and then x squared will be cubed, which will give you x to the 6th power, right? Yes? So what if I do g is composed with f? What will happen now? What will be g composed with f?
f से आउटपुट के लिए वो रियल नंबर है, तो g भी इनपुट जा रही है वो इंटीजर.
Many, the domain is not completely defined on the domain.
So the first thing you do when you talk about function, you say what is its domain, what is its codomain, right? Yes.
Sir, here R is not a subset of Z, so we can't really build numbers.
That's a good point. R is not, so we have to be careful about the domain and codomain, right? Remember, we don't want the codomain to be subset of something. We want the range to be subset of something. So we may still be able to do it. I'm not saying you can, but the requirement is not Z to be a subset of R or R to be a subset of Z. Requirement is like in this case, maybe the perfect squares have to be a subset of something, or perfect cubes have to be a subset of something. Yes, please. Yes. It's a good thing. So suppose f is a function which works on all integers, right? F is a function. So, his question is, why the range of G is required to be only a subset of F? Why is not the range of F, why don't we ask range of F G to be equal to the domain of F, right? Most probably that was your question. So, what was I saying? Suppose F is a function that works on all integers, right? You give it any integer, it does something, it takes the 6th power or the 7th power, right? And G is a function that works on all integers, it returns the squares. It's integer to integer, it will return you square, right? Now, what I am saying is that F must be capable to work on the output of G. This is this statement. F must have the capability to operate on the output of G, right? So, in the example I was saying that if G gives squares, then for composition purposes, for the purpose of composition, we only want F to be capable of working on perfect squares, while it could be actually be able to work on any integers, right? Perfect squares are supposed to be positive or non-negative numbers, right? F may work on all integers, negative, positive, small, big, right? F may be trained to work on real numbers. But what cannot happen, that there is an output of G on which F cannot operate. If F operates on infinitely many numbers, but missing out on one output of G, just like in this case, look at this, what is the capability of G? What can G work on? G only is trained or is coded for, it's built for working on integers, right? It's trained to be working on integers. Now, what if F outputs something real number? So, suppose what is G composed with F? Supposedly, this G circle F would be a function from, what will be the domain of the function? Yes, this will be the function. So, now I am asking what will be G composed with F on 3.41? 3.41, I will apply F on it first. 3.41 F, what does F do? F cubes it. So, it will return something like 31, let us say. Okay? It will return 31 or 30 or whatever 3 square root of cube of 3.4 is. Then we will apply G to this 31.4. What will be the output? 31.4 squared is not going to be the output. G only works on integers. Okay? So, this is the case where it will not, we need this restriction has to be done there. Okay. So, G cross it. So, the range of the inner function, that is what we told earlier, this inner function must be a subset of the domain of the outer function. Okay. Let us see this one now. If F is the same function, maps integers to their cubes, and G is the same function, by functionality it is the same, it maps integers to their squares, right. What is F circle composed with G? What is F composed with G of some number x, some integer x? Yeah, that number raised to the power 6, right. That could be a positive number or negative number or any integers, right. What is F composed with G of 3.2? Yes. What is F composed with G of 3.2? That is not part of our domain, right, it is out of course question. What is G composed with F? What is G composed with F? Except for G first cubes it and then squares it. F composed with G first squares it and then cubes it, but in terms of output they are exactly the same. Okay? Not always though. Here is another function, a function which maps integers to their square, the same F, and G is a function that maps integers to their double. Okay? Their doubles, integers. What is F composed with G? What is F composed with G of A? We will first apply g to a. So, how do you say it in English? What is f composed with g of a? When input is a, what is the output of f composed with g, or what is the working of f composed with g? We will first double it, that is, we will apply g to it, right, and then we will square it. And what do we get from that? We will get 4a squared. So, in this case, f composed with g of x will be 4x squared, right. So, it will be f of g of x. G of x gives me 2x, and then f of 2x gives me the square of 2x, which is 4x squared. Is this clear? Okay. What will be g composed with f of x? How will it operate? It will first apply f, then it will apply g. To the output of f, it will apply g, right. So, if I give it a number x, what will it do? It will first square it, and then it will double it, right, by application of g. Okay. So, the output will be g composed with f of x will be 2x squared. Are they the same? They are not the same. What can we conclude? F composed with g is not necessarily the same as g composed with f. In the previous case, when f was x squared and g was x cubed, right, in that case we can commute them. They are kind of commutative. You can flip the order, either first apply g and then apply f, and in this case we cannot, right. Is it clear? So, in some cases we may be able to just compose, we may be able to do in any order. That is what the associative law or the commutative law of addition and operations are, right. This operation is not commutative. Okay. So, sometime in the first example we saw the other side, the f composed with g was a function, g composed with f was not even a function, right. That is the r and f problem was there. Okay, it was not even a function. So, if it is possible, sometime it may be possible in both direction, but not they may not be equal. Okay. Okay. So, everyone knows what is function composition. Okay. So, now let us play with it and just see what if I compose a function with itself. I have a function, another function I can compose. The only requirement is you can compose two functions, and there are certain restrictions on the domain and codomain. So, what if the function in the same function, I write it twice and then can a function call itself in computer programming? Yeah. What is that called? It's recursive functions, right. Recursive functions are just called. That is actually composition of function with themselves, right. So, let us do an example. Suppose I have a function that maps integer to their successor, right. That is actually the increment. This when in C++ you write x plus plus or I plus plus, that is what the increment function. So, it maps element to the successor. Okay. What if I compose it with itself? F circle f composed with f of x. That will be, you first apply f, assuming the domain codomain requirements are met, then you apply f again, right. So, in this particular case it will be you increment it once and you increment it twice. Okay. So, you see this? I do not know if you have seen this thing, but what is this thing? It is a composition of this increment with itself. The number of composition is actually this number, right. So, I could write here 5, right. This is the composition of increment function with itself 5 times. You can do this. Is this clear now? This is it for this example. We can also do multiple time composition. Okay, x composed with itself, f, some function f composed with itself multiple times. So, if I compose this function f composed with f composed with f, all we have to do, if you compose two functions, we get a function, assuming the domain requirements are met. I compose a function f with g, I get another function, let us say call it h. Then h can be composed with some function p, right? That can be composed with some function f3, and just I can continue doing this. There is nothing fancy there. This multiple composition is exactly the same thing. We have all the vocabulary for it, right? That is why if you think about it this way, f composed with f 3 times is actually basically f composed with this other function, which itself is a composition of f with itself, right? Just play with the parentheses, you can see this, and it's just repeatedly applying f a few times, right? So f of x will be x plus 3 for this particular value of f, okay? Sometime we will write it, okay, so this is a cool one. Suppose I have this father function. Again, there are issues with these functions, okay? This is not really, but it's easy for us to say, talk about this. This is about people who are just alive or who are somewhere in the record, right? It's a population. The issues with this function is, what if somebody's father is not alive? So what is this people function, this people set, right? If it's not alive, then it's getting an image in outside the domain, right, or something like this. So with those type of issues, just assume we are done with this. There is another issues, okay, so that will be a lot of theological discussions here. What is Jesus in this set or not in this set, or blah, 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 all this kind of nonsense, okay. So you don't you see that will be issue, right? Does he have a father, or where is the name, right? So, and then Adam and Eve, those are also there. That's like also an issue, right? So that's why last time when I introduced this function, I said with some understanding of this set of people. I can't say just set of people now. So if I say the set of people alive, then again it's a problem, right? That's like if somebody's father is not there, then where is the output, right? And then everybody has to have a mapping, right? So this purpose is just so that we can talk, right? And this is the best way of saying this is the best way to demonstrate recursion, or what is it called? Function composition or recursion, yeah. So father of x is a function. You give it a person's name, and it will give you the name of the father of that person, right? So what will be father of x? It will give you the name. You ask that you input a person's name, and it will give you the it will output the grandfather of. What will be father of x? Right, and that will be the great whatever grandfather. Okay, so now if I can compose function with themselves, I can compose function with other functions. For some function, the inverse is also a function. So what if I compose a function with its inverse? Right? This self-destructive argument. So let's see what happens here. Suppose I compose a function with their inverse. What will happen? What do you think will happen? Right? And this is now you look at this formula. Where is this formula? Right? A will give you B. F will convert A to B. F inverse will transform B back to A, and you will end up with nothing, right? You will end up with identity map. Okay, F is.
So we can only compose functions with themselves or with their inverse when their domain and codomain are the same?
Well, that's a good thing. Good question. Would we always be able to compose a function with its inverse? Would we always be able to compose a function with would we always be able to compose a function with themselves, a function with itself? So you have to be careful with that thing. You have those restrictions will always apply if you are composing a function with itself, right? So that's one thing. Would we always be able to compose a function with its inverse? Why?
Because the domain of the inverse is the set of images of the initial function, which will always be the range or the code.
Yeah. So if a function is what is it called? Invertible. It's a bijection. then we know what is the domain in the codomain, right? They are very closely related to this, right? So, f and f inverse, what is the domain? I told you somewhere there, the domain of the inner function and the outer function. So, but if the same thing, same function, we have to be careful with that. Okay. So, if a function is returning to me the negative square roots, suppose a function is returning to me the negative square roots of function, that was the one we saw earlier, right? Can I compose it with itself? Because the first time I give it a number, it will give me the negative square root of that number. But then the next time, we will have a negative number. I can't apply, I get the square root of a negative number, right? So, okay. So, this is what we see for the increment function. The inverse is actually a decrement function, and if you apply increment and then decrement, you will just crossing the bridge and coming back, right? So, this will, you will definitely get A to C. Okay. So, this was the summary. We have to get to the actual part of this course, which is this lecture, which is the one after this, relations. There are some functions that we really need a lot in computer science, in engineering, in mathematics. Some of you was one of you was very anxious about this increasing function the other day, about one-to-one. So, we will talk about that. So, these are numeric function, right? Numeric function generally mean functions which work on reals, numbers, right? In some time in computer science context, we restrict ourselves to integers also. Some, especially when we do cryptography and number theory, there we work in all group theory, all algebra generally assume integers. This discrete type of work on group theory and stuff. They work on some symbols, and reals are infinite sets but countable. And so, but generally when we say numeric function, that means reals, yeah? Either the domain is real or the codomain is real, or both are real or something, and sometime it could be integers too. So, these are called numeric functions. One good thing about numeric, which is in the next session we will learn, is about their ordering property. They are what's called totally ordered sets. We will learn that word later. The real numbers in the codomain, the integers, are totally ordered set, in the sense that every pair of numbers, every pair of elements in R or in Z are comparable with each other. You give me any number, any two numbers, you can ask me, I will be able to answer, is A bigger than, is one bigger than the other, or they are less than or equal to, or they are greater, or they are equal, right? That is not true about many sets. If I give you two apples, are they comparable? If you remember, at first day we did this thing at a lot of computer science, or this theoretical computer science comes down to this thing that I can compare numbers, integers, I can compare even negative numbers also, I can compare real numbers, I can compare negative real numbers. But the moment I go to two-dimensional numbers, I make it an array of two numbers, and then I need to, did we talk about it? I think we did, no? I remember writing something on the board. So, the moment there are two numbers, which one is bigger? We do not know. We need to come up with a definition, we need to come up with a criteria to say this. So, not everything. Two students, are they comparable? It depends, how do you compare them, right? You want to look at their GPA, you want to look at their age, you want to look at their stupidity, what is that? That's the criterion, right? You need to come up with that. Real numbers, integers, they are comparable. That's really cool thing, right? It's a totally ordered set is a really important thing, right? So, when you have a totally ordered set, then you can plot them. You can actually visually see that, right? And then we can say these kind of things, okay? So, a function, generally a numeric function, or a function mapping reals to reals, is called an increasing function if whenever the input increases, the output also increases. Is it clear? It is an increasing function. If I increase the input, the input value, it increases the output values. Okay. Now, I can talk about increases the input, increasing the output, right. I cannot say this thing, let us say, about non-comparable stuff. Is this clear? This is how we write it. For any x y, whenever x is smaller than y, then the output on x is also smaller than the output on y. Okay? F of x is less than f of y whenever x is less than y, right. In other words, if I increase the input from x to y, the output increases from f of x to f of y. Okay, that is why it is called increasing function. Actually, yeah, okay. So, this less than or equal to makes it what we call increasing function. If instead of this less than or equal to, it was strictly less than, then it will be called strictly increasing function, right. So, technically these functions are called non-decreasing function. Okay. And there is analogously we define decreasing function and non-decreasing function, strictly decreasing functions. Okay. It's clear? This some words. These functions generally are called monotonic functions, right. There is just one tone, their derivative is just in one direction, they are either positive derivative or negative derivatives, right. The descent, not the derivative, is the vector thing of this. So, that is what is increasing and decreasing. Here is how you would write them. Look at this function. This is called an increasing function because whenever an input is increasing x1 to x2, it goes bigger, the output goes from x1, and this is true for any x1, x2. Anywhere in this range, in this plot I see, whenever x1 is bigger, the x2 is bigger than x1, then f of x2 is bigger than f of x2. Here is a function, look at this, this is not increasing, this is not even monotonic, because in this interval it is increasing. If I go from this point to this point, the input goes from this point to this point, the output goes from here to here. But in this region, in this interval, then it is decreasing. So, this increases, then decreases, then it increases, then it decreases, right. It is not a monotonic function, it is not increasing, neither decreasing. This is a decreasing function. No matter where throughout this horizontal line, whenever I go to the right, the function values goes less than equal to, go down, right, in less than equal to sense. And this is a constant function, it neither decreases not increases, it just stays fixed constant function. Okay, strictly increasing, strictly decreasing functions are by definition actually one to one. Okay, that is what some of you said last time. Was it you? I asked somebody and I said, is the function one to one, and they said yes, the function is increasing. Was it you? Okay, idiot. Okay, so okay, so increasing function. Now, two more functions that we are going to talk about, and this is detailed. Then we take a break for a few minutes, and then we come back to relations. Okay. The floor of a function, everybody must have seen floors, right? Rounding, round up, round down, and round to some number of precision digits or something. It's a function. Now we are not talking about rounds and stuff. Those are just very vague things. The floor of a number, a real number, is the largest integers that is smaller than x. The floor of x is the largest integer that is smaller than x. Okay. The ceiling of x, it is denoted by this thing. So, how would you write it in Excel? Slash in not Excel, LaTeX. You will write it as slash L floor slash R floor slash L seal slash R seal. The floor of x is the largest integer that is smaller than x, and the ceiling of x is the smallest integer that is bigger than x. Okay. In real line, if you want to find this floor of a function of a number, you look at the left side, you start going to the left. Which is the first integer that you hit? That is called the floor of this number. Okay. For the ceiling, you look at the number on the real line, start going to the right, increase. What is the first integer you hit? that is called the ceiling of the number. Okay? Yes? So, this is how you draw the function, plot a function. This is a numeric function, we can plot it. So, this is the ceiling. What is the ceiling of 2.3? 2.3, you start going to the right, the first integer you hit is going to be your answer. So, it is 3. What is the floor of 2.9? The ceiling of 2.9. What is the ceiling of 2.95? Still 3. You see, for all in this interval, all the values are 3, right? This is 3. This is how the plot is. I got this thing from Wikipedia, and similarly the floor. Okay, so you know the stuff, and you should do this thing. The next thing is exponentiation. All of you should know this, everyone. I just want to, because when we do recursion in recursive algorithm, we are going to come across them a few times. So, just wanted to tell you, everyone knows log. Is there anyone who doesn't know logarithms? Okay, so log is just the inverse of the exponentiation function. You exponentiate a number, an integer to another integer, or some another have to be integers. Neither the base nor the exponent is required to be an integer. You just a to the b, you define b to the x. If you reverse that, that will give you x back for the same b. So, that is log. Log is a very slow growing function. So, this is what you will hear a lot in your data structures in algorithm course. Log is a slow growing function. Look at this thing. So, please look at this thing. Okay, this is a very small scale, but what is log of 1? 0. Any base, right? So, let us say it's base 2. This is base 2, right? Yeah, it's written there. So, log base 2 of 2 raised to the power 0 gives me 1. So, that is why log base 1 is 0. Log base 2 of 1 is 0. Okay. You see, I multiplied the input from 1, I multiplied the input to 16. How much the output grows? The output just goes 4 times. Here I went 16 times, output goes 6. Suppose I multiply in, so what is log base 2 of 1024? 10, right? The input went from 1 to 1024, and the output would go only from 0 to 10, right? That is what we mean by a slow growing function, right? It is a very, very slow growing function. The derivative is, what is the derivative of log 1 over log x? 1 over x, right? It is just the more the x grows, the slower it goes, 1 over x. That is what you see, it is very slow growing function, right? It is log n, there are much slower growing functions. This is a very fast growing function. You see, I barely double the input. What happens to the output? Gets 4 times. I double the input, I went from 2 to 4. What happens to the output? It went from 4 to 16, right? The exponentiation is a very fast growing function, right? If you do algorithms with me, the first thing you will hear this, what's the title of the first session, one of the sessions in the first lecture is the curse of exponential runtime of algorithm, right? How bad it is if your algorithm has exponential runtime. If your algorithm runtime is 2 to the n, you are doomed, right? For only, other than for n equals 3, 4, 5, you can't do anything. So, the rest is just basic logs thing. You should do this. This is very important thing for information theory, or you must have seen this stuff in your computer architecture type stuff. If you want to write, what is the maximum number you can write in 10 bits? The maximum unsigned integer that you can express in 10 bits. 2 raised to the power 9 unsigned bits. So, you can just express any number between 0 and 1023, right? 2 raised to the power 10 minus 1, right? That statement is written here. how many bits will you require to express 1027, 1014? How many bits, unsigned integers, we are talking about how many bits will you require to, okay. What is the range of number that you can write in, what did I say, 10 bits? So, in 10 bits, what numbers, what in 10, let me just write, what unsigned numbers, integers can you express? 0 to, let me just write it 0 to 2 to the 10 minus 1, right? That is what 1023. Now, I am asking the reverse questions. How many bits do you need to write, to express this number? This is, by the way, 10 to the, what is it, 1023. Can you do it in 9 bits? But this theorem says in 9 bits you can only do from 0 to 511. 2 to the 9 minus 1 is 511. How many bits do you need? You need 10 bits for these, okay. That 10 is this log of 10, right. So, this is this 2 to the 10. If you take log base of this number, you will get 10 out of it, right. So, log base 2 of 2 to the 10 is equal to 10, right. Log base 2 of this 10 is something like 9 point something, right. You take the ceiling, and that is what it is, that is the statement written there, okay. Log of the floor plus 1, that is a better way to do it, floor plus 1. Okay. So, relations is another very important concept and topic in this course. It is a generalization of function. It is used a lot in computer science. How many of you have heard of databases? What do you know about database? Sorry, can you please say it? How many of you have done some work in database, heard about it, some? What is the technical way to refer to a database system? DB, DBMS, RDBMS, that is the correct word for it. Fully correct word is RDBMS, right, because there could be many databases. There could be graph database, there could be text database, NoSQL database, there are these what is it called, XML databases. So, the word that SQL database is called relational databases, okay, relational database. A relation in that sense means just a table, okay. It is exactly this relation, okay, that relational word is this relation, which is just a generalization of functions, okay, in ordered pairs. So, pay attention to this. You are going to need, I do not know if you have done, but when you do one of the most technical part you will see in database is this query optimization is one thing, query optimization. That is exactly what you do when you do logical equivalence. You write a query, some formula, some predicate which are matched by something and which are not matched by others. You try to reword it differently, it will become a different query, it will take much significantly less time or more time, or it will give you better results or something, right. So, that is one thing. The next thing, big thing is there is called join, outer join, inner joins, right, and this is a very important thing. That is actually, that is all database, there is nothing more to it. The rest is just reporting and some other database administration. The science part is just query and projection and join, some operations. Okay. Remember this thing, a database is called a relational database, table is called a relation, right. A table is these things are called rows or records or data items, or right, and the columns or types of these are called fields or columns or attributes or coordinates and this kind of things. So this is a database is an ordered n tuple. If it has n columns, then it's called ordered n tuple. It is in every row is an ordered n tuple, right? The ordered tuple, the first coordinate is a name, the second coordinate is GPA, the third coordinate is physics grade, the fourth coordinate is computer science grade, and so on, right? This is why, and if you combine them, then it becomes a relation, it becomes a table, okay? Look at this thing. What does this tell you? What does this picture tell you? What does this picture tell you? Huh? Exclusive OR? What does the picture tell you? Exclusive OR? Huh? It's
For these bits, like I'm repeating them as bits, but it looks like XOR gate.
it's XOR gate, but
It actually is mod 2 addition. So
mod 2 addition.
1 or 0.
Yeah, yeah. So it's addition. It's binary addition. So it does XOR gate type thing. XOR gate basically remove the carry. Otherwise, this is what. How would you add 2 bits? Right? 0 plus 0 is 0. 1 plus 1 is 1 0. So you keep 0 and the 1 carries to the next bit, right? In the additions. Okay. What is this? How did we use these diagrams? What did we use this type of diagram to represent? Is this a function? Okay. What is this? It's students in their courses registration. What is this? Do you guys know what is these things? It's recently changed. You don't know? You know this?
Yes, sir.
What is it?
It doesn't exist anymore.
It doesn't exist?
Yeah, they rebranded Twitter to X.
No, the next one.
Instagram.
What is the next? This is all the stuff that are really good. So let's see what do all these 4 things have common. These 4 pictures you saw, what do they have in common? The shape? Where is shape? Do you think this shape is the same as this shape? No, not these 4s, these 4s. What do they have in common? They relate, yes. Yes, they all, everything represent data. I mean, if I draw a computer here, that would also represent data, right? Yeah.
Every element of one of these has some specific relation to one another.
Yeah. So look at the first one. This is when you saw this picture, I asked you, what does it remind you of, right? This representation. You said function. They're more like function, right? There is some violation. What is the violation? E is not mapped to anything. C is mapped to 2 if it was a function. It's not a function, but it looks like that, right? The first one can be thought of as a function. So this is ID. So, but here the domain is now ordered triples of a set of names cross the set of departments cross the set of GPA. Now f of 43211 is equal to, it returns, remember we said a function is from a set to another set. That set could be set of images, set of computers, set of hostel rooms, set of ordered triples, set of ordered pairs, set of vectors, set of videos, right? Whatever it just gives you an output. Output type is your choice. Right? So if I say that that this is a function where this set of IDs is the domain in the name cross departments, cross CGPA is the codomain, then this is a function actually, okay, unless there are other restrictions, okay, unless there is an empty row or something like this. But anyway, they all relate certain things with other things, right? They don't relate, they are actually anti-relation stuff, but they think they are called online social network, right? This is they are built to destroy societies. No thing. This was very one of the days is people were arguing with me. By the way, I work a lot with these Facebook graph and the Twitter graph and this kind of bullshit. So, yeah. but that's I do, but I don't use them as such. What was I going to say? What was I going to say? So these are the most useless things ever. Okay, these things are very useless. How many of you use Facebook? How many friends do you have on Facebook? Huh? Just give me numbers. 200? How many? 100? How many friends do you have? 300? Huh? Okay. So you guys use it. I was going to say something, but let's see. We'll talk about this. Remember this function. I will remember. It will remind me. A function is a mapping given to sets x and y. A function is a mapping from x to y such that every element of x gets mapped to exactly one element of y. Right? That was the working definition of function, but actually technically we said that a function is if we represent it as a set of ordered pairs, image pre-image image pairs, right, then it can be thought of as a subset of ordered pairs, some ordered pairs of x cross y, the domain cross codomain. A function can be thought of as a subset of ordered pairs in domain cross codomains, right? The restriction that everybody must be mapped and everybody must be mapped to exactly one can be thought of is every element of x, the domain, must appear exactly once as a first coordinate. Okay, remember this definition of function, way of looking at function. So a relation is basically just taking off that restriction, that a relation is just a subset of x cross y. It's called a relation from x to y or relation from x to y. This was a mapping from x to y, a function from x to y. It's a relation from x to y. Just take any subset of x cross y. What is x cross y? What is x cross y? The Cartesian product. What is it? What is x cross y? Somebody. The set of ordered pairs. So what does, if you don't mention the word, if you don't utter the word x and y, you didn't give me a definition of x cross y.
Where the first element is a set belongs to a set x and the second element belongs to a set y.
Yes. What is x cross y? Yeah, cross product. What is cross product? Sorry, order two tuples. Chale.
It's all possible pairs that can be made such that the first element is from x and the second is from y.
Yes. So the set of all possible ordered pairs where the first coordinate, the first element comes from the set x and the second coordinate comes from the set y is called the cross product of x and y, right? Now this is a subset, there are a lot of elements there. If you this is a set, right, a set of all ordered pairs. If you take a subset of it, then it's called a relation. Okay, it's called a relation. Now let me just show you the examples. This is a relation from x to y. It's called binary relation if it's a relation from x to y, which is the relation between two sets. We could have relation on multiple sets, right? A relation that's called n-ary relation. We'll talk about it later. This n is called the degree of the relation. What's the degree of a binary relation? 2. right? Degree of a ternary relation is 3. It involves 3 sets, right? It relates elements of 3 sets. Yes, बोलो पिछला slide का क्या
x
हुआ?
क्रॉस y क्या represent कर रहे हैं?
Cross product, Cartesian product,
Vectors के दरमियान
vectors के दरमियान. Didn't we talk about Cartesian product? Ordered pairs, the set of all ordered pairs. वेक्टर्स के दरमियान कोई नहीं होता, सेट्स के दरमियान होते हैं. वो भी वो कार्ट प्रोडक्ट भी सेट. So vectors are elements of the Cartesian product. 2D vectors are element of this, the Cartesian plane, right? Okay, we can you can go home, and this function's first set of slides is about dot product, cross product. Okay, so that's a domain. So is this thing called database? Is it a subset of the set of names, all possible names or names appearing in LUMS, cross the set of IDs, cross the set of departments, cross the set of numbers between 0 and 4? Yes. Okay. You know what is x cross y? X cross y, we talked about it last time. So if you have a set X, it has element A, B, set Y, which has element 1, 2, 3. I think this is exactly the example there. The set X cross Y is a subset of a set of ordered pairs A1, A2, A3, and what else? B1. This is the cross product. Is it clear to you too? Okay, this is the cross product of x cross y, the Cartesian product, right? You take all possible ordered pairs where the first element in the ordered pair comes from this set and the second element comes from this set, right? Now, it's a set. I can take its subset. You take any subset of it, that's called a relation. Okay? How many different relations are possible from x cross y? How many different relations are possible from this x to this y? 6? 2 raised to the power 6, y 6, 2 raised to the power 6.
So there are 6 elements in this set of x.
In the cross product, there is 6 elements. So the number of subsets of the cross product is 2 raised to the power the cardinality of the cross product. So in this case is 2 to the 6. Okay? Is this clear? So that's a relation. This is called a relation from x to y, right? Because it's a subset of x cross y. It could be a relation from y to x if it's a subset of y cross x. If you remember, we said that last time that y cross x is not the same as x cross y unless x or y or one of them or both of them are empty, or x or y are the same, right? Generally speaking, they are not the same. So these things, every element here is, what is it? A 4 tuple, right? Every row here, every record here in this database are 4 tuple, right? It has 4 fields. The first field is an element of the set names. The second field, the second coordinate is an element of the set of IDs, and the third element, the third coordinate is an element of the set of departments or programs, and the third element is a element of set of real numbers between 0 and 4. Right? Is it true that every element is an element, every row is an element of this set? Right? It's a 4 tuple, which is, so that's why these 4, 1, 2, 3, 4, 5, these 5 records or this database is actually a subset of this cross product, right? And we call this a relation. It's a relation from set of names, 2 set of IDs, 2 set of departments, 2 set of real numbers between 0 and 4, right? We will talk about multi-dimensional relation. Right now, we are talking about binary relations only. This is a relation because it maps or it relates 2 numbers to their output, right? A set of 2 numbers to their outputs. So 0, 0 is related to 0 because when I add 0 and 0, I get a 0. When I add 0 and 1, I get a 1. When I add 1 and 0, I get a 1. And when I add 1 and 1, I get a 0. Right? That's how I define it, and that's how I can represent it. This is more of a Zambil or RO record, and this is not a function because of this multiple mapping or somebody not getting mapped, but it is a relation. It could be, it is a subset of the set of students cross the set of courses, right. All of these elements here, A, DM, A is a student, DM is a course, B, A calc, B, DM, C, DM, C prog, and all of these are ordered pairs. The first element come from the set of students, the second element come from the set of courses, right. All these elements, this is a subset of this set, right. Hence, this is a relation. It's clear? That's a definition of relation. Just take a few, or just a collection of ordered pairs, then we call it a relation, right. It becomes extremely important in this. That's why I told you this. I gave you the example of database because I wanted you to remember that the word is relational database, and this is that relation. Okay. Okay. Some terminology. Suppose I have a set X containing these 5 elements A, B, C, D, E, and the set Y containing these 3 elements calculus, DM, programming. Here is the relation. It is a subset of X cross Y. I can write it as a set notation any way you want me to describe. I know multiple ways to describe sets. You can use either of them, right. Set builder notation, set with a predicate, with some English description, or just give me the list of the elements. Here I am giving you list of the elements of this subset, that is this relation. We pronounce it, the right way to do it is ADM is in R. ADM is in this set R. Is it true? Is ADM in R? Is BDM in R? Yes? Is EDM in R? No, it is a set. Some elements are there, some elements are not there. I know how to check membership of elements in a set. Right. So, I generally say this thing, this is more correct terminology. Sometime you can also write A is related to DM, if it is clear that this is related. So, A R DM, right. Or if you more computer science jargon is this thing, R, when I input A and DM, it gives me true, right. If that is R A D M is true, or 1, or R E D M is false, R A D M is true in this case, right. So, it is one way or the other. I have to tell you whether the pair is in the set or not in the set, right, depending on your. So, we can say B calc is not in R, E is not related to any. If it was a function, E must be mapped to at least 1 and exactly 1. Here E is not related to any, right. So, it is not a mapping, function mapping. A and C are related to more than 1 elements, right, they are both related to 2. But that is okay, it is not a functions have no such requirements, relations have no such requirement as functions. Here is how we can represent a relation, just exactly as we did functions. Is a relation from X to Y can be represented by drawing X on the left side, drawing Y on the right side. If an element of X is related to some element of Y, or if that is, it makes an ordered pair with some other elements in the relation, then you draw an arrow between them. Okay. So, for example, this relation will be A will have a arrow to DM and 1 arrow to calc, B will have an arrow to DM and 1 to no more, C will have an arrow to DM and an arrow to prog, and D will have an arrow to prog only. Is clear? Ordered pairs, I just have to give you the pairs ordered. Where is the order information here? This is the first coordinate, the arrow head is the second coordinate. Which is the pairing information, it connects 2, right, it makes 2, it involves 2 things, the arrow goes from one thing. So, there are many other applications, many applications of relations that we will study. When we did function, we did a function from X to Y, right, but X and Y could be the same, right. We saw function from real to real, right, we saw function from integers to integers, didn't we? So, similarly a relation also from X to Y, we can also have relations from X to X, relations from A to A, from y to y, right? Nothing wrong. As long as it's a valid set, then it will be a relations, and this will be ordered pairs, where the first coordinate comes from the set and the other second coordinate comes from the other set. Those are called the domains of the relation, by the way. But when this is the same set, we don't say it's a relation from A to A. We say it's a relation on the set A, right? It's a binary relation on the set A. So that makes it clear that it is a relation from A to A, or a subset of A across A. Okay, so a relation on the set X. That's just a word. A relation is called reflexive. Okay, let's just stop at this point.